This example will compare the response of a rotating machine and an inverter-based resource to a grid fault in EMT simulation. It's based on the test harness that was used in the PSCAD breakout session on August 3rd for a 100 megawatt solar plant connected to a 230 kV grid with an impedance of 10 ohms at an angle of 85 degrees. There are a couple of transformers involved. There's a step down to 33 kV collector system, and then another step down transformer to 600 volts inverter. The transformer, the plant transformer, the 100 MVA transformer, I believe had no resistance, but we added some resistance, so the impedance is 1 plus J12%. In the EMTP breakout session, we used a wind plant, which have increased the size to a compatible 100 megawatts. The collector system is slightly different. It's 34.5 kV. The inverter voltage is a little bit different. The step-up transformer, the wind turbine is a little bit different. There's also a equivalent of the medium voltage collector feeders. It didn't appear in the solar farm example, but that's okay. That's not going to make that much of a difference. And then we're going to run one of those two, depending which tool you had, and then we're going to compare that to a 100 megawatt synchronous machine with an H constant of 3 seconds. Typical step-up transformer generator step-up unit. You see the winding configuration is a little bit different. On the generator side is a delta, and 20 kV on the low voltage side there, but still the same 1 plus J12% impedance. The machine electrical parameters actually came from an 892 MVA unit for the IEEE subsynchronous resonance, the first benchmark test system. A couple things we want to illustrate here, especially for the synchronous machine. We would like to initialize its load flow to match 100 megawatt power export. So in magenta, I've indicated the terminal bus of the machine where we would like to have 1 per unit voltage and 100 megawatts export. We can solve that within a kind of a simplified equivalent circuit using this formula, pretty well known. P equals V1 V2 sine delta over X, where delta is the power angle across the reactance, so we're ignoring resistance there. V1 and V2 are approximately 1 per unit, so basically we can solve for delta. And the way the system is laid out, when we solve an EMTP, we're going to set 1 at an angle of 0 degrees at the point of connection here on this bus. Okay, so the reactance of interest is the J.12, which is the reactance of this step-up transformer, 12%. When we do the PSCAD solution, you can specify the angle of the voltage behind the source impedance. So that's what we'll do in PSCAD. And so then the reactance of interest is this J.12 plus J.0189, and that is the reactance of the 10 ohms on 100 MVA and 230 kV. So we get a couple of different angles depending on the tool. Minus 23.1 degrees for EMTP and minus 22.016 degrees for PSCAD. The difference there is caused by this, whether or not this reactance is included in the initialization. The other thing I want to point out is that this is a delta Y transformer where the delta winding is going to lag by 30 degrees. And so when you calculate an angle here, when we go back to the machine terminals, we're actually shifting minus 30 degrees through that delta Y transformer. That's what we have to account for. So the angle at the terminal with respect to 0 degrees is positive, but we subtract 30 to get the angle that we're going to input to the simulation in the EMT tool. And I'll show you that when you do your breakout session for the tool that you're using. The other thing I want to look at on this slide is how we should set the reactance of the fault, JXF. So most of the faults, as you know, are resistive, but here what we want to do is simulate, actually in the simplified grid equivalent, we want to simulate the effect of a nearby fault, which is going to cause a certain amount of retained voltage at that point of connection. So for now, we're going to look for a voltage down to 50% of normal. So retained voltage of VDF of 0.5 per unit. You can see the voltage divider circuit, and again, we're just considering reactances, and we're ignoring, the reactance, the voltage support provided by the synchronous machine or the IBR plant. We're just ignoring that. We're ignoring resistance, so we have a simple voltage divider reactances, and then we can solve for X or L, depending on which tool we're going to use, whether we're going to input henries or reactive ohms. And as you can see, if we want a higher retained voltage, the reactance in that bulb is going to be higher. But for now, what we're interested in for 50% retained voltage is either 9.96 ohms or 26.42 millihenries. The other thing I wanted to discuss is more detail on how we're going to use ComTrade in the ComTrade recorder. So we only record 10 channels, and that should be enough. We're going to get the 3 currents coming out of the IBR plant or the machine, IAFT, IBFT, and ICAT. That's these here. And we're going to pretend there's a current transformer CT connected to the plant exit. We're also going to have at the point of connection CCVTs or just VTs, but they're going to measure the 3 instantaneous voltages, VA, VB, and VC. So we're going to get waveforms out of there. We also have some sensors during the simulation that are going to calculate the RMS voltage, the real power, the reactive power, and the frequency. Some of these models, for example, you would have the phase lock loop, an estimate of the frequency coming out of the plant, if it's an IBR. You can also get a plot of the machine speed, if it's a rotating machine. But actually, we're interested in the frequency estimate at the point of connection, and so that's why we're calculating here at the location shown. The RMS is also an interesting quantity. You can, in either of those tools, you can measure RMS values independently on each phase. You could also try to measure the positive sequence voltage. Those are going to be different. But we do see sometimes is this estimate of the RMS voltage, and it can be calculated instantaneously, as a function of time, from the instantaneous values of the 3 phase voltages. Basically, you take the average of VA squared plus VB squared plus VC squared divided by 3 and take the square root of that. That gets you a pretty good estimate of the RMS voltage, at least under balanced conditions. Now, if it's not balanced, you're going to get some oscillations. But one of the tools, if you put in the RMS sensor, it actually behaves that way. And so we're going to try and match that in the second tool. The other thing I wanted to talk about is how you lay out your channels in for ComTrade export. So one of the tools, PSCAD, exports in kV, KA, megawatts, and megabars. So those are more convenient for power systems work. EMTP exports in volts and amps, watts and bars. And that's no problem. We can handle it in post-processing, but I thought would be interesting is suppose we want to put them on a common base. So we're going to follow the PSCAD convention, and in post-processing we want kV, KA, megawatts, megabars, and hertz. So in this table, which we provide on the GitHub repository and in your download in a spreadsheet, but we're calculating the scaling factors and the offsets to use in EMTP. So we're going to put in the scaling factor and the offset for, say, the voltages. So 11.46, and the offset is 0 because the instantaneous voltage is going to be symmetrical around the y equals the axis. But in the 2013 version of ComTrade, we set it up so that the integers can, integer values, which are what's stored in ComTrade, is minus 32767 to plus 32767. The ComTrade data file is going to have an integer within that range. You multiply that by A and add B, and you will get volts. If I want kV, I'm going to divide it by this primary transducer ratio. So most of these are 1E3, except for P and Q. We call it what megawatts and megavars, so I want to divide watts and bars by a million to get megawatts and megavars. And then for the frequency in hertz, both tools export in hertz, so there's no adjustment there. So this is what's going on in the spreadsheet setup, and it'll make more sense to the EMTP folks when we set all this up in that tool, so that we're going to get export in compatible units, so that the units are using K and M as multipliers in both tools. The next thing you'll do is download the example model files and scripts for this module. This is the GitHub repository page. We sent this link out before. It's in your slide deck. But I reorganized the downloads into this tabular format. So the pre-session from July 27th and the plant level session from August 3rd, those files are the same. They're just reorganized in this table. We come down here to this example: combined rotating machine and IBR behaviors in EMT. That's the module we're talking about now. Your slides are under this link. The models are under this link. And then the 3 videos are going to be under these links here. So what I'm going to do is click on this link here for models. So it's going to take me to a file that's 472 kilobytes. The way to download this is over here next to the word raw. It says download raw file. And I'm going to click on that. And I'm going to navigate to a directory I'm going to use the same one each week. It's under my temp directory. And I made a directory called I2X, and I'm going to download, I don't want the one there really, that's from a previous test file. So I'm going to download this right here, and what I've done is I'm using the same directory as for the August 3rd session. So what you'll be able to do each week is update the files in this directory. If it's the same one each week or each session, then it'll be saved to override. If we override any files, it'll be because there was a reason to. So you won't destroy anything that you were working on. But if you do work on something, modify one of the scripts that we provided, one of the models that we provide, please just save it under a different name or a different directory so you don't overwrite. But we're doing it this way because some of the supporting files, like the contract support files, we had to make a change this week, and that may happen again. So we are going to assume that they may be upgraded. So let me see if I can get my window back on the screen. You can see it. So I'm just going to hit save there, and it did. Yeah, okay. Now in Windows Explorer, I have navigated to the directory, or just saved that zip file. What I'm going to do is open it with my utility, and I'm going to let's back in here. I'm going to extract it, not to temp I2X MachineIBR, but I want to go straight to temp I2X. And it is going to start asking me if I want to replace existing files. So here's one. This is the Solar library, which is a dependency of PSCAD. It's okay to overwrite this. So notice the dates and the times are the same. It's okay to overwrite that. This is the ComTrade Python file. Now notice that the dates and the size is a little bit different. So I want to overwrite it. And everything else was new. So now we're set up. You have a new directory here. This is the support directory. This has the the spreadsheet file that had the source and fault impedance calculations, the angle for the machine terminal, initial condition and the comp tray channel setup. So this file will expand with more worksheets in that workbook. You may be interested in that. Okay, now your next step, now that you downloaded and unzipped the files, if you're following along, is to go to one of the next videos. So I went back up one directory in GitHub, and you're going to use either the EMTP video or the PSCAD video, depending on which tool you're following along with, and then we'll go through how these are implemented in each of those respective tools.